Question 2 is a fixed asset that you will have seen in many of my topical playlists. It's basically asking you to think about the thermal stability of group 2 nitrate. We know that the group 2 nitrate essentially, well, they wanted us to write a question afterwards anyway, so I'll just write it to show you what it forms first. So I give you the group 2 oxide, which is M2 plus and O2 minus. It give you 2 NO2 and it give you half O2. I've done this equation a lot of times that I know it balances out this way. If you want, you could multiply by 2, you get 2, 2, 4 and 1. So the ratio of NO2 to O2 is 4:1. They want us to state and explain the trend. I typically like to explain first. Essentially how you explain it is down group 2. So down group 2 there are more filled inner shell. So as a result of it, your size of cations, so the ionic radius of the cations, the M2 plus increases. When your radius of cation increases, M2 plus become, well, the charge density will decrease. Charge density of M2 plus decreases as the ions remain +2, still +2 charge. So size is increased, but +2 charge is still the same. Therefore, the charge density decrease. M2 plus cations become less polarizing. So the cation is polarizing, it becomes less polarizing on the NO3 minus ions. So therefore, the NO covalent bond is less weakened. So you are not weakening it that much. Therefore, more difficult to decompose since it requires a lot more energy to break that NO bond since it's not very polarized by the cation. So more difficult to decompose. And if it is more difficult to decompose, what I can say is it becomes more stable to heat. So the thermal stability of the group 2 nitrate would increase. They become more stable to heat as they are more and more difficult to decompose. Question 2, part B1. This is basically asking you to do the exact same equation as I've done above. So lead 2 nitrate decomposes the same way as group 2 nitrate. They'll give you lead 2 oxide, Pb2 plus O2 minus. They'll give you NO2 and they'll give you O2. 2 of the nitrate will give you 2 of the NO2. When you count the oxygens, there are 6 oxygen atoms on the left. Here you've got 1, here you got 4. 4 plus 1 is 5. You want 6 altogether on the right. So this is oxygen molecule, so you need a half there. They don't ask for stat symbols, but this would be a solid, giant ionic structure. This as well, solid. This is a brown gas, and this is a colorless gas, which you can't see obviously. Now they say how would the ease of decomposition compare with barium nitrate? You're supposed to use the data booklet. Based on the essay that we have written in part 1, we're supposed to compare ionic radius. So let me just go straight to the page on ionic radius. We are comparing ionic radius, so make sure you choose the right one. The ionic radius of Pb2 plus, I wonder if I'm given Pb2 plus at all. I am not given the Pb2 plus. Let me just double check again. Period 2, period 3, group 2, group 14. Yes, I am given it Pb2 plus under group 14. So the radius of Pb2 plus is 0.120 nanometer. This versus the radius of the barium 2 plus, as they're asking us to compare to the barium compound. There are 2 entries in barium in the group 2. Make sure you choose the one with the Ba2 plus because we are comparing ionic radius. Okay, so be careful based on the essay that you have written previously. So going back to the original question, so Pb2 plus is smaller, so it's got smaller ionic radius than Ba2 plus. I've already used my data booklet and quoted the values for the ionic radius. Therefore, this thing is more polarizing. They are not, they do ask you to explain your answer. So Pb2 plus is more polarizing than Ba2 plus. Polarizing is on the nitrate, So if it is more polarized than the nitrate, therefore PbNO3 twice is easier to decompose, because based on the previous essay, if you are more polarizing on the anions, the NO bond is more weakened, so the lead to nitrate is more easier to decompose than the barium nitrate by using the data booklet. Next up, question 2, C part 1. We have barium ethane dioate, which comes from ethane dioic acid. So this is Ba2 plus C2O4 2 minus, and it decomposes to give you barium oxide and a mixture of two different gas. So obviously you don't get NO2 here because there's no nitrogen to begin with. We get two different gas. They are not telling us what gas it is, but they are different gas. I imagined it would be carbon dioxide, but then if I just produce carbon dioxide, my oxygen doesn't balance out, and I can get oxygen, but I'll get too many oxygen on the right side. So I think actually it could be O2 actually, because then you have one barium and one barium, two carbon, one carbon. Oh yep, carbon doesn't make sense there, so it can't be anything without carbon, because the moment I put 2 there, I have 4 plus 1, which is more oxygen than what I need. So I cannot have 2 CO2, I must have 1 CO2, but this leaves me 1 extra carbon here. So different gas. Carbon as a solid is graphite diamond, so it can't be carbon. As a gas, it could be carbon monoxide. 1 barium, 2 carbon, 1 and 1, 2 carbon. Oxygen, 2, 3, and 4. I've got 4 oxygen. I think this equation is balanced now. All right. Question 2, C part 2. So I have a bunch of these. It's a percentage by mass question. It's a percentage composition by mass. So it's not related to the equation I've written before. So redox reaction takes place, all the barium ethane dioate reacts, and what is happening here is let's see what's going on. Redox reaction, blah 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 blah. So first of all, you have barium ethane dioate, and then you react it with MnO4 minus acidified. A redox reaction takes place and all the barium C2O4 reacts, and then this thing is with excess of this, so and then you will have unreacted MnO4 minus, and it is this thing that you do another titration plus iron 2 plus aqueous. This is an oxidizing agent, so any remaining bit of it can oxidize iron 2 to iron 3. So we have 2 redox equation here. So let's start from the very end. So your first equation is going to be MnO4 minus plus 8H plus there are 5 electrons involved, so I need 5 Fe2 plus, because then they will give me 5 Fe3 plus, and they'll give me another 5 electrons on the right side from the third equation that's shown in the on your question paper, which you know where to find obviously without me telling you to, and this will give you Mn2 plus 4H2O. What I've done is I've combined to give you the full equation by multiplying the iron 2 and iron 3 equation by 5, and you get 5 electrons on the right. They will cancel the 5 electrons on the left for the reduction of the manganese plus 7 to manganese plus 2. From there, I can work out my mole ratio. So what do I want? I want the mole of the MnO4 minus is to the mole of the iron 2 plus, and I have 1 mole of iron 2 plus reacting with 5 mole of iron 2 plus from the balance equation. And what do I get? I get at the bottom, I have the volume of the iron 2 plus, which is 30.40 cm cube. I do it in dm cube by multiplying by 10 to the minus 3, because n equals to Cv, the concentration is in mole per dm cube, so your volume of solution must be in dm cube. I don't have this information on the manganate, and in fact that is what I want to find. This is how much manganate remains at the end of the reaction unreacted. Okay, so the mole of the manganate unreacted in the first reaction, unreacted from first reaction is going to be equal to, just bring up all that thing, 1/5 times 30.40 times 10 to the minus 3 times 0.0500. Press that onto your calculator. Oops. And I get 3.04 times 10 to the power minus 4 mole. Anyway, so what other information am I given? I was told how much manganate I use in total. In total, which is in excess, I have 50.0 cm cube, but I also have 0.0200 mole per dm cube. So the mole of the KMnO4 reacted in the first reaction is going to be the total KMnO4 that I react, which is 50.0 times 10 to the minus 3 dm cube times 0.200. This is how much I put in based on the question. This is in excess. How much MnO4 minus reacted in the first reaction is going to be this total minus how much remained. How much remained at the end of the reaction was what I did for my second titration. So this amount from the second titration was actually how much unreacted. Take that away from the total that you put in for the KMnO4, you're going to work out the mole of MnO4 minus reacted in the first reaction. So it's minus 3.04 times 10 to the power minus 4 mole. So that very first bit, 50.0 times 10 to the minus 3 times 0.02, I get 1 times 10 to the minus 3, and then minus that previous answer. Now I have 6.96 times 10 to the power minus 4 mole of KMnO4 that actually reacted in the first reaction. What else do I know in the first reaction? I know that in the first reaction, so it's KMnO4 reacting with manganate. If you compare the first two redox equation given, so C2O4 2 minus going to 2CO2 plus 2 electrons, MnO4 minus plus 8H plus 5 electrons, giving you Mn2 plus 4H2O. Without writing the whole balance equation, which I really don't need to, there are 2 electrons here, there are 5 electrons. I'm going to do lowest common multiple, which is a primary school mathematics. So LCM of 2 and 5 is actually 10. So you're going to multiply the top equation by 5 and the bottom one by 2, like that. And then you will get the mole of C2O4 2 minus is to the mole of MnO4 minus. So you're going to get 5 times ethane diovate ions, and then you're going to get 2 times MnO4 minus. Okay, so that's how I can get my mole ratio. And in my part 3, which I'm going to continue down there, I will just paste that. And this is how much reacted in the first reaction between the ethane diovate ion from the barium ethane diovate. I want to know the mass of the barium ethane diovate that reacts. Okay, so the mass, the mole of the BaC2O4 give you the C2O4 2 minus. So the mole of barium ethane diovate is the same as the mole of that. So the mole of that is going to be equal to the mole of barium ethane diovate. So what I can do is I can just sub this out, and I have BaC2O4. So I want the mass of barium ethane diovate in the pure sample. So I have the mass of barium C2O4 divided by the MR. So obviously I need the MR of BaC2O4, which is given very conveniently in the question, 225.3, so I don't need to waste time and do that. So that's my mole of barium ethane diovate on top. At the bottom is how much MnO4 minus reacted in the first reaction, which was what I did in my difference there. Total KMnO4 put in minus the KMnO4 left at the end of the reaction that you do titration with iron 2 plus. 6.96 times 10 to the minus 4 mole. 6.96 times 10 to the power minus 4 mole. So you can rearrange your equations before you press your calculator. You're going to bring that up. So you're going to get 5/2 times 6.96 times 10 to the power minus 4 times 225.3. And I got my final answer as 0.392022 gram. This is the mass of barium ethane dioate in the sample out of 0.5 grams. So the percentage of barium ethane dioate is basically 0.392022 out of 0.500 times 100%. So I got my final answer 78.4044. I should run out my final answer to appropriate number of significant figure, which in this case is 3 significant figure. If you look at the mass given, 1 significant figure, 2, and then 3 significant figure. Of course, you can also give it to 4 sig fig, given that the titer given for the KMNO4 was 30.40 cm3, so 3 or 4 significant figure is entirely acceptable for the 4-mark question. The very last bit of this 12-mark question, so let me just think back. Was that question 2 or was that question 3? So that was question 2. We know that barium hydroxide, well, it says completely dissociated. We know typically the pH of barium hydroxide is around pH 14 because it's very, very soluble in water. It's a very strong base. So it's going to give us Ba2 plus and 2 OH minus based on the stoichiometry in this balance equation. So what you have is you have 0.120 mole per dm cube. So what happened then is 1 mole of these will give you 1 mole of that and 2 mole of that in the same volume. So this is just dissociating to that. Therefore 0.120 will give concentration of OH minus as 0.120 times 2, which is 0.240 mole per dm cube. So that's your first job. If your OH minus is 0.240, then we can work out Kw equal to 1 times 10 to the power minus 14 equal to H plus times OH minus. And I want to find my H plus concentration, so 1 times 10 to the power minus 14 divided by OH minus concentration, which is 0.240. So you might do it in a slightly different method, but you might realize that at the end of the day, you probably have the exact same method as mine. It's just in a different form. So once you get the concentration of H plus, pH equal to minus log 10 of H plus. So your previous answer, just take the log 10 and put a negative, and it's a sensible number. They don't tell you how many significant figure, but look at the data given. 1, 2, and 3 sig fig in the data given. 1, 2, and 3 sig fig in the data given. Back in topic 1 in AS chemistry, they did specify the candidates, A-level candidates must know what is appropriate number of significant figure given the data and the precision of each particular question. Okay, so that's it for that 12-mark question.